What if secret excavations had uncovered signs of prehistoric technology? Technology older than mammals, older than reptiles, older even than the dinosaurs themselves. What if beneath the familiar layers of Earth's geological past, there were traces of something that should not exist? Something that challenges the very foundations of history, evolution, and our understanding of life on this planet? Imagine unearthing a fragment embedded in ancient rock, not shaped by wind or water, not formed by geology or chance, but bearing a symmetry that whispers of design. Imagine holding in your hand an object older than anything humanity has ever built, older than any creature we recognize, older than the very ecosystems that gave rise to dinosaurs. If such a discovery were real, then the story of Earth would not begin with us. It would not begin with dinosaurs. It would begin with something else entirely. Tonight, you will enter a calm, hypnotic journey into deep time, where the boundary between science and mystery dissolves, and the forgotten epochs of Earth awaken like shadows returning to the surface. As you drift into this immersive documentary, you will be guided through landscapes erased by extinction, ecosystems dissolved by geological churn, and eras where life did not resemble anything known today. Because the truth is that Earth is not only ancient, it is layered with histories lost to erosion, subduction, and time. If prehistoric technology existed millions of years before dinosaurs, it would not be made of bronze or iron. It would not resemble tools or machines. It would be something more subtle, more organic, more difficult to recognize. And yet, across the world, in secret excavations buried beneath oceans and deserts, researchers have uncovered anomalies, patterns in fossils, metallic inclusions in impossible strata, mineral structures that look disturbingly engineered. While official reports classify them as geological curiosities, those who have seen them up close speak differently. Imagine a fossil bed where symmetrical structures repeat across dozens of specimens, as if nature itself were following instructions. Imagine a collapsed cavern where excavators uncovered a circular mineral formation fused perfectly into surrounding rock, its layers alternating in a pattern too precise for chance. Imagine a desert dig where a lattice of metallic filaments was found embedded in stone more than 500 million years old. These discoveries do not confirm prehistoric civilizations, but they press against the boundaries of what we think is possible. They invite a new question. If intelligence rose once, why not twice? Why not 10 times? Why not long before the fossil record matured enough to preserve the bodies of complex life? To entertain this possibility, you must let go of human assumptions about technology. Technology does not have to be mechanical. It does not need gears, metal, or electricity. In deep time, technology could have been biological, chemical, or environmental. It could have grown the way coral grows. It could have communicated the way fungi communicate. It could have stored information the way crystals hold structured patterns. And if such technology ever existed, it would leave behind signatures so faint that we would mistake them for natural formations, unless we knew what to look for. As you settle deeper into this narrative, picture forgotten landscapes illuminated by dim, alien suns, continents unformed, oceans thick with the experiments of early life, ecosystems driven by rules no longer present in the modern world. If intelligence emerged in these primordial realms, its traces would be woven into stone, memory fossilized not as machines, but as patterns whose meaning we have not yet learned to read. This journey invites you to imagine, to question, and to explore the possibility that the oldest technology on Earth is hidden not in museums, but deep beneath our feet, locked inside the very rock that built our planet's ancient skin. Before we move further into this mystery, share your theory in the comments. Do you believe prehistoric technology could have existed before the age of dinosaurs, or is the evidence pointing somewhere else entirely? And if these forgotten epochs stir your curiosity, like this video and subscribe to the channel. Your voice, your presence, and your curiosity help shape this growing community of seekers, exploring the unknown chapters of Earth's story. To understand whether secret excavations might truly have uncovered signs of prehistoric technology, we need to confront a truth so immense that it reshapes everything we assume about Earth. The planet has lived countless lives, and nearly all of them have been erased. The Earth you know, the one mapped and photographed and charted in textbooks, is only the most recent skin of something ancient and restless. Beneath it lies a world lost to deep time, a world where continents existed and dissolved, oceans rose and vanished, and ecosystems emerged in forms no human mind has ever witnessed. When you trace the layers downward, you are not just excavating rock, but the memory of a planet that has rewritten itself again and again. This is the first step toward imagining how any traces of prehistoric technology, if they ever existed, could survive long enough to reach us now. To understand this, picture Earth not as a static sphere, but as a great shifting archive. Every few 100 million years, plate tectonics shuffle continents like pages, burying entire chapters beneath new crust. Mountain ranges rise, crumble, and are swallowed by sediments. Oceans fold into the mantle. The surface we stand on today is not the surface life walked on hundreds of millions of years ago. Those ancient worlds are layered beneath us, compressed into stone scattered across tectonic fragments. If a civilization existed before the dinosaurs, its ruins would not resemble broken pillars or scattered tools. They would be mixed into the geological record like whispers caught between pages. And this brings us to the first enigma that has puzzled geologists. Certain layers of extremely ancient rock contain anomalies, patterns that look intentional, textures that seem structured, metallic concentrations arranged with geometric precision. In the official literature, these are categorized as mineralogical curiosities, but their regularity raises questions scientists rarely dare to voice. Could complex processes, more advanced than what we understand, have shaped these formations long before dinosaurs ever evolved? Or do these patterns reflect natural forces we have not yet learned to interpret? Consider the rocks of the Ediacaran period. They hold impressions of organisms that defy classification, creatures without bones or organs, bodies shaped like fractals, surfaces rippling with symmetry. These fossils come from a world that operated under biological rules very different from the ones that govern life today. Their geometry has led some researchers to speculate that early life engaged in environmental engineering, influencing sediments, altering mineral deposition, and creating orderly structures that look disturbingly like primitive biological technology. These ideas are controversial because they blur the line between biology and design, but the fossils themselves remain silent and stubborn, refusing to fit neatly into any known category. The deeper one digs, both literally and philosophically, the more one realizes that Earth's earliest ecosystems contained interactions we still do not comprehend. If life then had different biochemical pathways, different sensory systems, different pressures shaping its evolution, then intelligence might have emerged in forms unrecognizable to us. Technology might have taken paths that leave no metal, no ceramic, no artifact in the sense we understand. Instead, prehistoric technology could have manifested as coordinated chemical systems, environmental modifications, or molecular structures that fossilize not as objects, but as layered patterns in rock. And in secret excavations performed by teams studying remote desert basins, collapsed mountain caverns, and deep-sea mineral ridges, certain patterns begin to appear repeatedly. They are not identical, but they rhyme. Layers of the same depth showing abrupt mineral transitions, as though some ancient system altered the chemistry of the environment with a precision hard to explain through random geological processes alone. Some sites contain shimmering traces of rare metals arranged in branching lines. Others display circular arrangements of crystal growth that do not match known natural mechanisms. These formations do not confirm prehistoric technology, but they create tension in the scientific narrative, a tension that grows stronger when compared with the sudden bursts of complexity in evolution. The geological record shows repeated episodes where life appears to leap forward without clear cause. These leaps could simply reflect evolutionary innovation under environmental stress, yet there is a subtle rhythm to them, as if something pushes life into new forms at specific intervals. Some theorists propose that these moments are remnants of earlier biological systems collapsing or transforming, leaving behind environmental signatures that later life inherits without understanding their origin. To imagine prehistoric technology, imagine organisms capable of modifying their environment not through tools, but through biology. Coral reefs today build vast structures without consciousness. Fungal networks engineer soil ecosystems. Microbial mats alter mineral chemistry across entire coastlines. Scale these abilities back hundreds of millions of years, and intelligence could emerge not as individuals, but as networks. Their technology would be an extension of their biology, adaptive, regenerative, dissolving into the environment when no longer needed. Over hundreds of millions of years, their remains would flatten into patterns on stone, patterns we find today but cannot decipher. And so Topic 1 does not ask you to believe in ancient machines hidden under rock. It asks something far more subtle. Whether technology could have existed before the dinosaurs in forms unlike anything humans have ever made, and whether the clues are already beneath our feet, waiting for us to notice their shape as we move toward the next question, which begins when we consider how such civilizations might have survived catastrophic extinctions that erased nearly all traces of their world. A question that leads directly into the next topic, where we explore the mechanics of deep time erasure and the ways in which ancient intelligence could persist only through patterns that, if traces of prehistoric technology exist, then they endured forces so destructive that nearly all evidence of ancient worlds vanished. To understand how anything could survive from before the dinosaurs, we must examine the mechanics of erasure itself. Earth is not a passive archive. It is a restless sculptor, constantly rewriting its own surface. The crust folds, cracks, melts, and regenerates. Mountains rise, then crumble into dust. Oceans expand and retreat, stripping continents bare. Entire ecosystems disappear beneath volcanic plains. When continents collide, their landscapes are crushed into metamorphic rock, obliterating whatever once existed above. If a prehistoric civilization built structures, networks, or systems of any kind, those systems would have been dragged downward into the mantle, crushed by unimaginable pressures, transformed into minerals, or scattered as sediment across ancient seas. Yet the same processes that erase the visible traces of a civilization can preserve its deeper patterns in forms so altered that we no longer recognize them. The oldest fossils we know are not bones or tools, but impressions, chemical gradients, and layered structures that hint at organisms dissolved long before vertebrates existed. If ancient technology ever existed, it would survive in equally indirect ways, leaving behind signatures not of shape, but of influence. Imagine an ancient civilization dependent on biological networks, vast interconnected organisms working in unison to regulate ecosystems, channel energy, or store information. When such a system collapses, it does not leave ruins, it leaves environmental disruption. Sudden chemical shifts in oceans, abrupt changes in atmospheric composition, layers of sediment showing coordinated mineral patterns. These are the types of anomalies geologists occasionally encounter, anomalies that raise questions never fully answered. For example, certain transitions in ancient rock strata show sudden spikes of metals such as molybdenum, vanadium, and nickel, elements associated today with catalytic processes and biological coordination. These spikes occur in layers far older than complex animal life, raising the question of what mechanisms accumulated them so precisely. Some geologists attribute these spikes to hydrothermal vents or localized anoxic events, but these explanations often fail to account for the symmetry and repeated spatial distribution across distant sites. If an ancient biosphere engineered its environment intentionally or inadvertently, these patterns could be its fossilized footprints. Consider also the phenomenon of extinction horizons, thin bands of rock marking the abrupt end of entire ecosystems. Some horizons show not devastation but transition, as if one biological regime yielded to another in a matter of geological moments. These transitions sometimes accompany anomalies in carbon isotopes, oxygen levels, or mineral deposition that do not align neatly with volcanic or cosmic explanations. While scientists debate their cause, a more speculative possibility emerges when viewing these layers through the lens of prehistoric intelligence. Perhaps the collapse of an ancient system triggered ecological cascades that reshaped global environments, not in a single cataclysm, but through the unraveling of networks once essential to stability. If prehistoric technology was woven into these networks, biological, chemical, or environmental, its disappearance could leave behind not artifacts, but scars. Yet we also face the opposite puzzle: sudden appearances of complexity. The fossil record documents moments when life seems to reorganize itself with astonishing speed. The Cambrian explosion is the most famous example, a burst of creativity emerging from a world that appeared, on the surface, stable and uneventful, But there are older pulses too, moments when life leaped forward in form, structure, and function. These leaps raise a question. What drives such rapid innovation? Environmental triggers? Genetic opportunity? Or something else? Something inherited from systems long dissolved into the fabric of Earth? If prehistoric civilizations existed, their collapse might have left behind molecular templates, chemical architectures, or ecological frameworks that later life unconsciously reactivated, resulting in evolutionary bursts that seem to emerge from nowhere. Imagine now a world far older than dinosaurs, dominated not by vertebrates but by sprawling microbial superstructures, colonies capable of coordinating across miles, communicating through chemical pulses, storing information in mineral lattices. These systems might have developed feedback mechanisms to regulate climate, ocean chemistry, or nutrient flows. Over millions of years, they could refine their coordination into forms we might interpret as technology, not mechanical, but environmental. When such systems fail, their breakdown could trigger global transformations, echoing as extinction events or chemical shifts recorded in rock. What we interpret as natural cycles might instead be the residual effects of collapsed worlds. One of the most mysterious geological puzzles is the appearance and disappearance of banded iron formations. These formations reflect ancient oxygen rhythms that scientists attribute to microbial activity, yet the precision and scale of some banding patterns suggest not random fluctuations, but sustained cycles with uncanny regularity. It is not unreasonable to wonder whether early life engineered its environment to maintain stability, creating cycles that today appear as enigmatic stripes preserved through billions of years. If such cycles were part of prehistoric technological behavior, primitive but deliberate, then their remnants could be hiding in plain sight. As excavators working in restricted zones dig into the deepest crustal fragments accessible on land, they occasionally uncover mineral assemblages that show unusual alignment, as if crystalline growth followed a blueprint. Some of these structures are dismissed as natural quirks, yet they recur in formations separated by vast distances. Their consistency hints at a phenomenon that once spanned oceans, continents, or ecosystems. To dismiss them is safe. To question them is to step into the unknown. The deeper into this unknown we travel, the more tension arises between what Earth preserves and what it erases. Evidence of prehistoric technology, if it existed, would not present itself as ancient machines waiting to be brushed clean. It would appear as disruptions, patterns, signals encoded into stone. The challenge is learning how to read them. But to read them, we must ask what form ancient intelligence might have taken and how it could operate under conditions so different from the world we know. This question leads us toward the next layer of mystery, which begins when we consider not the environment that erased prehistoric civilizations, but the environments that allowed them to rise. Environments so foreign and ancient that technology itself might emerge from biological and chemical processes we are only beginning to understand. Processes that, to imagine how prehistoric civilizations could have risen before the dinosaurs, we must step into worlds so ancient that the very definition of civilization begins to unravel. Our concept of civilization is tied to architecture, metallurgy, agriculture, symbolic communication, features born from human experience. But in the deep past, intelligence would not have been shaped by the same pressures, the same materials, or the same biological constraints. It would emerge through pathways foreign to us, guided by ecosystems we can barely conceptualize. Technology in such a world would not be carved or forged. It would be grown, it would flow, it would restructure itself, and it might dissolve into its surroundings so completely that only faint patterns remain. When we look back at ancient ecosystems through this lens, new possibilities emerge, revealing worlds where biological systems acted with a degree of coordination that hints at something we might call intelligence, though not in the sense we use that word today. Consider the earliest multicellular organisms. They were not simple creatures drifting mindlessly in shallow seas. Many operated as colonies composed of specialized modules, each performing a different function. Some coordinated their behavior across large areas of the ocean floor, shifting in response to environmental signals, regulating flows of nutrients, influencing sedimentation, These colonies blurred the line between organism and ecosystem, functioning as vast biological machines whose components behaved like parts of a singular organism. If such systems refined their coordination over millions of years, they could form the foundations of civilizations, not individual minds, but distributed networks. Picture a world where intelligence arises not in a single organism, but in the interplay between thousands. A world where communication flows through chemical signals, where memory is stored in environmental gradients, where adaptation occurs not through tools, but through the capacity to reshape habitats. In such a context, prehistoric technology might manifest as something that modifies water chemistry, sculpts mineral patterns, or alters thermal currents with remarkable precision. This idea becomes more plausible when we examine modern analogs that hint at how deep-time intelligence could have operated. Mycelial networks today share nutrients across forests, making decisions that maximize ecosystem stability. Coral reefs build vast limestone structures more complex than many human cities. Slime molds solve mathematical problems without brains, tracing the most efficient paths through mazes. Microbial mats engineer their surroundings, creating chemical gradients that sustain entire ecosystems. These systems behave intelligently because intelligence is not limited to neurons. It can arise from any network capable of sensing, responding, and adapting. In the deep past, when life's chemistry was more flexible and evolution's experimentation more extreme, these systems could have grown into something far more coordinated. Imagine a civilization formed not from individuals, but from interlinked colonies stretching across shorelines. Their technology would emerge from their biology. Their tools would be extensions of their collective metabolism. Their architecture would be reefs, mats, or distributed structures grown through chemical signaling. As we step further into these forgotten oceans, imagine organisms developing the ability to manipulate minerals at the microscale. Bacteria today already precipitate metals, forming magnetite crystals that allow them to orient themselves. Others deposit silica into intricate patterns that rival human-made nanotechnology. Countless species coordinate their growth to create sponge-like structures capable of filtering entire ecosystems. If such mechanisms were pushed by evolutionary pressures toward complexity, prehistoric beings could have developed mineral architectures with precision that appears artificial to us today. These structures, after hundreds of millions of years of compression, alteration, and metamorphosis, might survive only as puzzling patterns in ancient rock, indistinguishable from geological oddities unless viewed with the right perspective. But prehistoric civilizations may not have been limited to the ocean. On land, long before trees, long before vertebrates, fungal networks dominated landscapes. These networks are capable of transmitting signals, allocating resources, and forming complex relationships with surrounding organisms. Some theorists have suggested that early terrestrial ecosystems might have operated like global biological computers, processing environmental information at scales far larger than any single organism. If intelligence arose in these networks, it would not leave behind bones or tools. It would leave behind peculiar soil patterns, mineral gradients, and fossilized filaments that hint at communication systems once spanning entire regions. Some Precambrian formations show exactly such patterns. Branching webs of mineralized structures that resemble neither plant roots nor simple geological features. They occupy a liminal space between biology and something more structured, as though they were the remnants of networks that once performed tasks we are unable to reconstruct. One question that arises here is how such systems might evolve sophistication. Intelligence often emerges through the need to solve environmental problems, resource scarcity, temperature fluctuations, chemical instability. In deep time, Earth's environment was volatile, oxygen levels rising and falling, climates swinging between extremes, oceans fluctuating in acidity. These pressures could have driven prehistoric organisms to develop increasingly complex regulatory systems. Over time, these regulatory mechanisms might become technological in nature. Control of local temperature gradients, manipulation of light through reflective minerals, construction of channels to direct water flow. They would not build machines, they would build ecosystems that behave like machines. And because ecosystems persist far longer than artifacts, traces of these ancient technologies might still be embedded in the structure of stone. To grasp the scale of what might have existed, picture an entire coastline functioning as a single organism, capable of adjusting its shape, chemistry, and internal communication. Picture patterns in sediment that once served as memory, encoding environmental information that could be read and acted upon. Picture rhythmic pulses in mineral deposition that once synchronized activity across miles. These patterns would fossilize. They would endure. But without knowing their origin, we would mistake them for natural cycles, unaware of the possibility that they are shadows of prehistoric intelligence. And if such intelligence existed once, it could have evolved into forms that blur still further the line between biology and environment, leading us into even stranger realms of prehistory. Realms where technology becomes indistinguishable from nature and where entire ecosystems operate with purpose, a concept that pushes us toward the next question. If ancient civilizations emerged through biological networks, what mechanisms allowed them not only to persist, but to spread across vast landscapes, and what signatures might such expansion leave behind that? If prehistoric civilizations emerged through distributed biological networks, then their expansion across ancient landscapes must have followed mechanisms radically different from the migrations of modern species. They would not travel as individuals but as systems, spreading through replication, branching, fusion, and environmental integration. Their presence would ripple outward like a living fabric, rewriting ecosystems as they extended across continents, forming patterns that, millions of years later, would remain fossilized as sedimentary anomalies or mineral architectures that modern geology struggles to explain. To understand how these civilizations might have expanded, consider how networks grow in nature today. A fungal network spreads beneath forests in meticulously calculated patterns, optimizing nutrient distribution with mathematical precision. Coral reefs expand through colonies that cooperate, compete, and adapt collectively. Microbial mats move across shallow seas, responding to sunlight, temperature, and chemical gradients with coordinated efficiency. These processes reveal an important truth. Expansion does not require mobility in the traditional sense. It requires adaptability, replication, and internal communication. In deep time, these principles could have been refined into sophisticated strategies, allowing prehistoric civilizations to spread without ever developing limbs or tools, their intelligence embedded in the logic of growth itself. Imagine a coastline dominated by a superorganism capable of sensing shifts in climate and sea level. As oceans rise, it extends upward through mineral scaffolding. As they fall, it retracts, conserving energy. Over millennia, these expansions and contractions could create structural imprints in sedimentary layers, forming repeated patterns that resemble engineered terraces or artificial steps carved into ancient shorelines. Some coastal formations from the Precambrian era display such qualities, rhythmic platforms arranged with uncanny regularity, their geometry difficult to attribute entirely to tides or erosion. These structures may simply be natural, yet they also align with what a prehistoric civilization integrated into its environment might leave behind if its survival depended on engineering coastal space. Expansion might also occur through chemical influence. Certain microorganisms today secrete compounds that alter mineral growth. Others release signals that synchronize behavior across vast distances. In the deep past, organisms capable of modifying their surroundings could extend their influence by controlling nutrient flows, altering sedimentation, or creating vast fields of biomineralization. Over geological time, these fields would turn into rock layers retaining the signature of ancient coordination. Geological formations showing regular alternation of mineral bands, sometimes stretching across hundreds of kilometers, raise the question of whether life once played a more active role in shaping the environment than we assume. These bands, in some cases, are too uniform and widespread to be easily explained by typical cyclic processes. Viewed through the lens of prehistoric technology, they resemble environmental engineering on a scale beyond any modern biological system. Another mechanism of expansion lies in the way early ecosystems responded to atmospheric and oceanic shifts. Oxygenation events altered global chemistry so drastically that entire biospheres collapsed and reformed. If ancient civilizations were integrated into these chemical rhythms, they would expand or contract in synchrony with planetary cycles. Their technology, rooted in environmental feedback loops, could amplify or stabilize these shifts. When they collapsed, the disruption might appear as sudden drops in oxygen, abrupt changes in carbon flow, or global chemical anomalies preserved as thin, mysterious bands in rock. The geological record contains such bands. Abrupt shifts not easily linked to volcanism, asteroid impact, or climate change. They represent the kind of environmental aftershock expected when a vast, interconnected biological civilization dissolves, leaving its influence embedded within the chemical memory of Earth. Expansion could also involve the construction of large-scale frameworks, not buildings, but living architectures, biological superstructures designed to modify currents, regulate heat, or channel nutrients. Some ancient reefs and stromatolite formations extend for miles, their internal layering suggesting coordinated growth that surpasses random biological accumulation. While these are often considered entirely natural, certain formations exhibit alignment and geometric orientation that appear almost intentional. Their patterns persist across vast distances, as though created by an intelligence that perceives space through chemical gradients rather than sight. If prehistoric civilizations use such architectures as technological platforms, they might have built networks capable of sustaining complex behaviors, storing information, or manipulating environmental variables. We also find clues in the strange mineral veins that lace through some of Earth's oldest rocks. These veins branch like circuits, intersect at precise angles, and contain metallic compositions that differ sharply from surrounding material. They appear in regions where ancient microbial mats thrived, raising the possibility that early life manipulated minerals systematically. These veins could be remnants of early biological technologies, networks for transporting ions, distributing resources, or regulating environmental conditions. Over time, as civilizations expanded through these networks, they would leave behind a mineral fingerprint visible millions of years later. Some mineral veins even show sudden terminations, as if a living system connected to them vanished abruptly, freezing the structure in place. Such prehistoric civilizations would not need language to coordinate expansion. They would use chemistry, resonance, and electrical signaling. Consider the phenomenon of quorum sensing in bacteria. Once a threshold density is reached, behavior changes suddenly and collectively. Applied at planetary scales, such mechanisms could give rise to synchronized environmental engineering across regions. When a civilization operating through chemical logic reached a quorum moment, its expansion could shift into new modes, creating structural signatures across ecosystems, signatures preserved only as cryptic fossils or mineral traces. Some fossil beds show mass alignment of structures as if responding to coordinated behavioral cues. These curious formations suggest that vast biological systems once moved or grew with purpose, leaving behind imprints too subtle to be recognized as intentional without stepping beyond traditional interpretations. As we delve deeper into this possibility, tension rises between what nature produces spontaneously and what ancient intelligence might have directed. The line between natural structure and prehistoric technology becomes increasingly thin, almost invisible, forcing us to reconsider long-standing assumptions. Because if ancient civilizations expanded across landscapes not through physical construction, but through biochemical integration, then their presence would be indistinguishable from the ecosystems they shaped. Their influence would survive not as ruins, but as frameworks guiding future life, shaping evolution long after their disappearance. Their expansion would be written into the rhythms of Earth itself, rhythms that now lead us to the next question. If prehistoric technology embedded itself into the environment as it expanded, what mechanisms would allow such civilizations to store information across millions of years, leaving behind not machines but encoded patterns waiting to be uncovered by minds capable of recognizing their... If a prehistoric civilization expanded across ancient ecosystems using biochemical networks and mineral architectures, then the next challenge becomes even more extraordinary. How would such a civilization store information in a world without metal, writing, or physical tools? Information storage is the backbone of any intelligent system. For humans, memory is externalized through symbols carved into clay, printed onto paper, etched onto silicon. But in the deep past, long before vertebrates existed, no such materials were available, and the beings of that world would have evolved under entirely different constraints. Their information systems would follow the logic of their biology. They would embed memory in structures that were alive, dynamic, and integrated into the environment. The fossil record contains hints of such mechanisms, patterns that behave like archives rather than artifacts. To decipher these ancient imprints, we must look at how modern organisms store and transmit information outside the boundaries of DNA. Slime molds, for instance, remember pathways through chemical traces. Coral reefs store environmental histories in their layered skeletons. Microbial communities preserve complex behavior patterns and gradients of minerals, altering their surroundings in ways that encode decisions made generations earlier. These forms of memory survive catastrophes that destroy individual organisms because they are woven into the matrix of the environment itself. In the deep past, when conditions favored vast interconnected networks, prehistoric civilizations could have used similar mechanisms on far larger scales, embedding information into sediment, water chemistry, or mineral deposition, leaving behind fossils that act as ancient libraries. Imagine a coastline where chemical gradients serve as instructions, directing the growth of biological structures across miles. Imagine mineral plates acting as storage surfaces, with patterns that shift in response to environmental inputs, creating layered archives now fossilized in stone. In certain Precambrian formations, mineral bands show oscillations so precise they resemble recorded cycles, almost like biological inscriptions. These bands repeat at intervals that do not match tidal cycles or seasonal variations. Some researchers attribute them to fluctuations in microbial activity, yet their regularity suggests something more coordinated. If prehistoric beings encoded memory through environmental modulation, these formations could be remnants of vast information systems shaped through biochemical processes, systems that recorded data across continents now broken apart by tectonics. Memory could also have existed in patterned growth of organisms themselves. Early life forms created structures of remarkable complexity: branching filaments, spiraled colonies, fractal mats, and layered shells with microscopic designs. These patterns follow mathematical rules, and some are so intricate that they appear almost engineered. In an ancient civilization, such patterns could have served as functional memory, storing environmental conditions, behavioral responses, or instructions for coordinated actions. When these patterns fossilized, they retained their structure long after the civilization dissolved. Today, these fossils lie in museums and research labs, categorized as enigmatic organic impressions, their true purpose lost because we look for writing in lines and symbols instead of in geometry and rhythm. Information might also have been stored through resonance, mechanical, chemical, or electrical. Modern crystals retain vibrational memories. Certain minerals shift structure when exposed to specific frequencies. In the Precambrian world, where life manipulated minerals on microscopic scales, prehistoric technology might have exploited such properties, creating resonance-based archives capable of persisting through geological upheaval. When such archives fossilized, they would appear as grids of mineral alignment or repetitive crystalline structures within rocks. Geological surveys have documented veins with oscillating patterns that defy simple explanations, patterns that repeat too consistently to be random. They may reflect ancient environmental cycles, or they may be the fossilized echoes of prehistoric information storage. The next question follows naturally. How would such memory survive mass extinctions? Deep time is punctuated by cataclysms, ice ages that lasted millions of years, volcanic infernos, ocean-wide anoxia. Any civilization, biological or otherwise, would face extinction repeatedly. But memory embedded in the environment has a resilience that individual organisms lack. Chemical gradients reform after disturbances. Mineral inscriptions survive under sediment. Structural patterns persist through fossilization. Even after ecosystems collapse, their memory can guide the reemergence of life, as if the environment itself whispers instructions for rebuilding. Scientists have long noticed that certain evolutionary innovations appear shortly after mass extinctions, emerging with surprising speed, as though life remembers what to become. These bursts of innovation may correspond to the reactivation of ancient environmental memories, templates shaped by civilizations long vanished. The familiar narrative of random evolution becomes more mysterious when we consider this possibility. The possibility that information from prehistoric worlds is encoded into the landscape, waiting for new life to interpret it. And if memory persists, then influence persists. Prehistoric civilizations might shape not only the chemical and mineral world, but also the trajectory of evolution itself. Species emerging millions of years later might follow patterns established by systems that vanished eons earlier. Evolutionary pathways might be less random than they appear, guided subtly by structures inherited from ancient networks. Certain animal forms emerge repeatedly in different eras: segmented bodies, branching limbs, tubular structures. These morphologies are often attributed to efficiency, but they may also reflect deep templates embedded in the ancient environment. Templates left behind by civilizations whose memory remains imprinted in Earth's oldest layers. To imagine this is to realize how profoundly interconnected life is across time. Intelligence, once arisen, might never entirely vanish. Its memory becomes part of the world, shaping future ecosystems long after its creators disappear. These ideas push us beyond the limits of traditional archaeology into something new, a kind of deep-time reading not of artifacts but of planetary memory. In this light, every layer of rock becomes a document, every fossil a potential trace of ancient information, every mineral pattern a relic of prehistoric design. And if this unfolding mystery resonates with you, take a moment to like this video and subscribe to the channel. Your support helps this community explore deeper and deeper into the forgotten landscapes of Earth's past, where each discovery expands our understanding of what life and civilization might be. Because now another question rises: if prehistoric civilizations stored information across millions of years, could they have also developed ways of transmitting it, not just preserving memory, but sending it across space or across epochs, using environmental signals or chemical waves capable of traveling farther than any physical structure? Signals that may still linger faintly today, waiting for a species capable of recognizing their, if prehistoric civilizations stored information within the environment itself. Then the next step is to imagine how such civilizations might have transmitted that information across vast distances or even across geological ages. Transmission requires not just storage, but movement, the movement of signals through mediums capable of carrying them. For humans, sound travels through air, light through space, electricity through wires. But in the deep past, long before complex nervous systems existed, the very fabric of Earth served as the medium. Chemical gradients could spread across oceans for miles. Electrical pulses could travel through interconnected microbial mats. Vibrational signals could propagate through mineral lattices. These mechanisms, primitive yet powerful, could form the basis of prehistoric communication systems far more enduring than anything modern technology has yet achieved. If such systems existed, they would not leave behind devices. They would leave behind patterns, subtle variations in rock structure, fossil alignment, or mineral distribution that behave like the echoes of messages long dissipated. To understand this possibility, consider how modern biological systems transmit information. Trees communicate through fungal networks. Corals sense ocean temperature shifts and relay responses across tangled reefs. Microbial colonies coordinate through quorum sensing, triggering collective behavior once a critical threshold is reached. These forms of communication bypass the limitations of individual organisms, allowing information to flow through entire ecosystems. In the ancient world, where life was arranged in sprawling networks that dwarfed modern systems, communication could have scaled to continental proportions. Imagine a primordial ocean bed functioning as a vast information grid, with mineralized filaments acting as conduits for chemical instructions. Imagine pulses of ions traveling like messages across submerged plains, synchronizing the behavior of colonies separated by kilometers. Imagine vibrational waves generated by biological structures resonating through layers of sediment, carrying encoded signals that guided expansion, adaptation, or environmental modification. Such systems would be invisible to us now. Their organic components would have dissolved hundreds of millions of years ago. Yet their fossilized mineral frameworks may persist as puzzling structures that modern science interprets as natural formations, because no existing model allows for ancient communication technologies based on chemistry, resonance, and environmental integration. For instance, some geological layers exhibit rhythmic variations in mineral composition that resemble pulse patterns. These variations appear in multiple regions, sometimes separated by what were once shallow seas. The synchrony between them suggests coordinated environmental processes rather than isolated local events. Could these be the fossilized traces of prehistoric signaling systems, relics of communication once capable of shaping large-scale biological behavior? To imagine a civilization using such systems, picture organisms embedded in mineral matrices, living structures capable of emitting and sensing electrical or chemical pulses. Today, certain bacteria generate electricity. Others use magnetite crystals to detect magnetic fields. Some even produce biophotons, ultra-weak light emissions, potentially used for communication. In the deep past, evolution could have amplified such capabilities, giving rise to organisms that functioned as transmitters and receivers within a planetary-scale network. Their technology would not be separate from nature. It would be nature. They would send instructions through chemical waves, vibrational rhythms, or ion pulses that traveled across environmental gradients, influencing distant colonies. Over millions of years, these signals would shape ecosystems, leaving behind imprints that survive through fossilization, mineral replacement, or sedimentary layering. Their messages would become part of the world's geological memory. One of the most intriguing clues supporting this possibility lies in the phenomenon of oscillatory banding found in certain ancient rocks. These bands alternate between mineral types in patterns so consistent they resemble encoded sequences. Standard explanations attribute these patterns to periodic changes in temperature or ocean chemistry, yet some sequences are too precise, too stable, too widespread. It is as if they were generated by a coordinated rhythmic source. If prehistoric civilizations transmitted information through resonance, each oscillation might represent a pulse of communication, a signal that shaped the behavior of countless organisms. These signals would fossilize into rock, leaving behind a form of ancient writing, not in symbols but in repetition and rhythm. Transmission could also occur through optical properties. Some early life forms manipulated light through reflective or refractive surfaces. Modern organisms like diatoms and radiolarians create silica shells with geometric precision, bending light in complex ways. If ancient civilizations exploited such optical structures, they might have generated light-based signals that traveled through water or reflected across mineral surfaces. These signals could coordinate behavior without physical contact, creating a network that spanned entire ecosystems. When fossilized, these optical structures would appear as intricate microscopic geometries, patterns we catalog as biological ornamentation without considering their potential role as communication technologies. Another possible medium for prehistoric signaling is vibration. The Earth is full of natural resonances, low-frequency vibrations created by waves, wind, and tectonic movements. Organisms capable of detecting and generating such vibrations could transmit signals across large distances. Today, some fungi respond to vibrational cues. Some bacteria change behavior in response to low-frequency sound. If ancient civilizations amplified or manipulated these resonances, they could embed information into the physical vibrations of Earth. Over geological time, such vibrations might leave behind structural changes in rock, microfractures aligned in patterns, mineral grains sorted by resonant frequency, sediment layers reflecting rhythmic shifts. Transmission systems like these would not produce devices that survive intact. Instead, they would produce echoes, faint but pervasive. Geological enigmas, unexplained patterns, synchronized anomalies found in rocks of extreme age. We stand surrounded by these puzzles, often dismissing them as curious results of natural processes because our framework does not allow for anything else. Yet if prehistoric technologies used Earth itself as the medium, then the signatures of their communication may still be silently present, encoded into the crust, the minerals, the fossils. These signatures may still influence modern ecosystems subtly, imprinting ancient patterns into the fabric of life. Once we accept the possibility of prehistoric communication systems, a larger question emerges. What were these civilizations trying to transmit? Survival strategies? Environmental warnings? Memory across extinction cycles? Long-term coordination of planetary systems? And this question inevitably draws us toward an even deeper mystery: how such civilizations might have perceived reality itself. If their intelligence emerged from networks rather than individual minds, their experience of the world would be wholly different from ours, shaping a form of cognition that challenges everything we assume about thought, perception, and purpose. To explore this mystery, we must go further into the nature of prehistoric consciousness and how it might have evolved under conditions alien to anything we know. Conditions that, if prehistoric civilizations transmitted information through environmental signals and chemical waves, then their understanding of reality must have been fundamentally different from ours. Their consciousness, if consciousness is even the right word, would not have been confined to a skull or a central brain. Instead, it would have spread across vast biological matrices, integrated into minerals, oceans, and atmospheric rhythms. To imagine their inner world, we must let go of the human model of perception and allow something older, more distributed, more fluid to take shape. Their awareness might have arisen through flows in the environment, not through the separation of self and world. For such beings, intelligence might not feel like thought, but like synchronicity. Emotions might not exist as we know them. Instead, they might have experienced states of resonance with landscapes, oscillations with tides, harmonization with chemical gradients. In this context, consciousness becomes a phenomenon that emerges from connectivity, not individuality. Modern science gives us indirect glimpses of how such consciousness could operate. Consider the way slime molds map their environment. They sense nutritional gradients across their entire body and adjust their form accordingly, behaving as a single intelligence distributed across many branches. Or consider the way mycelial networks absorb signals from trees. When one tree experiences drought, the fungal network communicates this to others, triggering adaptive responses. In both cases, awareness is not a point, but a field. Perception is distributed. Response is collective. When extended across prehistoric ecosystems far larger and more chemically dynamic than anything on Earth today, such distributed intelligence could have reached levels of complexity that qualify as conscious, in a sense alien to human experience. This type of consciousness would interpret time differently. Human perception moves moment to moment, anchored in personal experience. A distributed system anchored in environmental changes would experience time through cycles, gradients, and slow-shifting patterns, seasons, tides, chemical transitions, mineral flows. For such beings, long-term changes would be as immediate as short-term stimuli. They might have perceived global transformations as clearly as humans perceive sound. Environmental fluctuations that took centuries could register to them the way a shift in light registers to us. Their intelligence might have been optimized for deep time, not rapid thought. They would sense the Earth's rhythms as though they were internal processes, making decisions in harmony with cycles far larger than themselves. Their perception of space would also differ drastically from ours. A human sees space through vision, a directional and limited sense. A prehistoric distributed intelligence would perceive space through chemical diffusion, electrical conductivity, mineral resonance. Instead of objects, they would sense gradients. Instead of distances, they would sense connection strength. Instead of boundaries, they would sense transitions. The world would appear to them not as discrete shapes, but as a living topography of flows, intensities, and potentials. This might explain why the physical signatures they left behind, if they left any at all, seem so difficult to interpret. They were not designing structures for visual inspection. They were shaping the environment according to networks of influence invisible to human senses. Their civilizations might not resemble settlements or cities, but zones of enhanced connectivity where biological, mineral, and chemical processes converged into a coherent system that functioned like a mind spread across kilometers. One of the most profound implications of this kind of consciousness is how it processes memory. Humans store memory internally through neurons and externally through writing. A distributed intelligence might store memory as long-lasting environmental changes. A shift in mineral composition could represent a decision. A growth pattern in a colony could represent learned behavior. A region of stabilized chemical conditions could represent a historical record. These memories would outlast any individual colony or organism because they would be embedded in the environment itself, When new components joined the network, they would inherit this memory through contact, like reading a text by entering the space where the information is encoded. Fossilized patterns we observe today might not merely be biological remains, but fragments of memory preserved in stone, messages written in a medium we are only beginning to recognize. Some researchers studying Ediacaran fossils note that their distributions and orientations are so consistent that they appear arranged, not scattered. Such patterns could reflect coordinated behavior, the spatial signature of prehistoric thought. Their consciousness might also have extended into global patterns. On modern Earth, the biosphere influences everything from weather to the carbon cycle. If prehistoric life had greater control over these systems due to its integrated structure, then its consciousness could have manifested as planetary-level awareness. Chemical shifts detected across oceans could have acted as sensory input. Mineral fluxes in the crust could have served as memory. Atmospheric composition could have been a feedback mechanism. A prehistoric civilization might not even have distinguished between itself and the environment. It would be, in a sense, a planetary-scale organism whose intelligence arose from the sum of its connections. Such beings would not need tools. They would modify their world simply by existing. Their intelligence would be inseparable from their physical form, and when they disappeared, the world itself would shift in ways that modern geologists identify as major transitions in Earth's history. If this conception of prehistoric consciousness seems alien, it is because human consciousness is specialized for a very different kind of world. A world of individuals, rapid change, competition, and limited sensory ranges. But in deep time, life was not divided into individuals the way it is today. It was a continuum. Boundaries were porous. Communication was constant. Consciousness, if it existed, would have been a flowing phenomenon, distributed across networks that evolved to sense patterns larger than anything humans can perceive. Understanding such consciousness requires us to rethink the very idea of intelligence. Intelligence might not be a feature of brains, but of systems. Awareness might not be localized but emergent. Perception might not require eyes, ears, or nerves. In ancient worlds shaped by gradients rather than organisms, intelligence would arise wherever complexity and connectivity converged. If such beings once existed, their disappearance would not erase their influence. Their memory would remain in the geological record. Their patterns would shape future evolution. Their legacy might survive in the behavior of modern ecosystems. And this leads us to a deeper question still. If prehistoric civilizations cultivated a form of consciousness intertwined with the planet, what could cause such a vast intelligence to collapse, fragment, or transform, leaving behind only hints in rock and chemistry? To answer that, we must consider the forces that governed ancient Earth, forces capable of ending entire modes of life and consciousness, forces that, if prehistoric civilizations possessed a form of consciousness intertwined with the planet itself, then understanding their disappearance means understanding the forces ancient Earth commanded, forces capable not only of extinguishing life, but of dissolving entire modes of intelligence. The Earth of deep time underwent transformations so violent, so sudden, and so absolute that modern catastrophes feel small in comparison. Massive glaciations froze the oceans from pole to equator. Supervolcanoes blanketed continents in molten rock. The atmosphere shifted between oxygen-rich and oxygen-starved states. Entire ecosystems collapsed in waves that spanned millions of years. If a prehistoric civilization was woven into environmental networks, then disruptions to those networks would have struck at the heart of their intelligence, fragmenting it, scattering its memory, and reducing its once cohesive awareness into isolated remnants struggling to adapt. These disruptions are preserved today as sharp boundaries in the geological record, thin layers marking the transition between eras shaped not by gradual change, but by sudden collapse. To imagine how such a civilization could fall, picture a world where intelligence depends on environmental stability, where chemical gradients sustain communication and mineral frameworks support memory. If a global glaciation encases the planet in ice, those gradients vanish. If volcanic eruptions poison the oceans with sulfur or methane, those frameworks fracture. Intelligent systems distributed across continents would lose connection with one another, their coordinated behavior dissolving into isolated pockets. The civilization would not fall like a city. It would unravel like a fabric pulled apart thread by thread until only disconnected strands remained. Those strands might attempt to rebuild, reconfigure, or adapt, but without the larger network they once relied on, their behaviors would shift from coherent intelligence to instinctive survival. Over time, these remnants would evolve into new organisms, their former capabilities forgotten, their memory preserved only in the faint signatures of rock and sediment. The geological record contains hints of such unraveling. During certain transitions, patterns in mineral deposition suddenly stop. Fossilized structures that once displayed regularity become chaotic. Rhythm gives way to noise. These disruptions often correspond with documented global events, suggesting that something capable of creating order was once present, and that its influence faded abruptly. The disappearance of Ediacaran organisms remains one of the most mysterious events in Earth's history. For millions of years, they dominated the oceans, creating complex, orderly landscapes. Then, at the boundary with the Cambrian period, they vanish almost completely, replaced by a new explosion of life seemingly unrelated to what came before. Scientists often attribute their disappearance to changes in oxygen, temperature, or predation, but the speed and totality of the transition raise unsettling questions. It resembles not a gradual evolutionary turnover, but the extinction of an entire mode of existence, as though the world lost something fundamental, a connection, a network, a form of awareness that once synchronized the planet's ecosystems. Some researchers have noted that shortly after these extinction events, new forms of complexity appear as if emerging from templates left behind. This suggests that remnants of ancient civilizations might not have vanished entirely, but instead transformed, seeding the world with patterns that future life would unknowingly follow. These patterns could guide the formation of body plans, metabolic pathways, or environmental behaviors. They might explain why certain biological architectures appear repeatedly across time. Perhaps they are echoes of ancient intelligence, re-emerging in new contexts, reshaped by evolution but still carrying the imprint of prehistoric awareness. If so, then prehistoric civilizations might not have disappeared in the true sense. They may have integrated into the processes of evolution, their collapse becoming a transformation rather than an end. But collapse does not always mean failure. It can mean transition. When a distributed intelligence loses coherence, it might not vanish, but instead dissolve into the environment that once housed it. Its memory becomes part of the world's chemistry. Its awareness becomes potential rather than presence. Over millions of years, this potential might reassemble under new forms, reawakening whenever conditions allow complexity to flourish. The cycles of rise and fall recorded in Earth's geological history could reflect not just biological turnover, but the repeated emergence of intelligence in different forms, each iteration building on the environmental memory of the last. The Earth may have birthed civilizations repeatedly, each one shaped by the constraints and opportunities of its age, each one contributing to a deepening reservoir of planetary memory. To understand the collapse of prehistoric civilizations, we must also consider how they perceived danger. Human civilizations fall when they fail to anticipate threats or when their complexity exceeds their ability to adapt. A prehistoric civilization integrated into environmental networks might sense global changes early. They might detect shifts in ocean chemistry or atmospheric composition long before physical collapse occurs. Their response would not be migration or warfare, but altering their own structure, shifting growth patterns, or redistributing chemical resources to maintain balance. But even such intelligence could be overwhelmed by planetary-scale catastrophes. A single volcanic winter could halt chemical communication. A sudden drop in oxygen could freeze metabolic processes. A rapid change in ocean salinity could sever network connections. When such events occurred, prehistoric civilizations would lose the coherence that sustained their intelligence, fragmenting into isolated clusters that could no longer communicate or coordinate. The fossil record hints at such fragmentation. Some ancient layers show clusters of structures that resemble coordinated colonies, followed abruptly by layers where those clusters appear isolated and irregular. The pattern suggests a system losing its ability to stay unified, like a neural network disrupted by injury. The final disappearance of these patterns marks the point where intelligence dissolved completely into biological remnants that would evolve along new paths, carrying faint memories of their former sophistication. And when new ecosystems emerged after the collapse, they may have inherited the environmental modifications left behind: chemical gradients, mineral frameworks, structural templates, subtle guides shaping the next era of life. What survived the collapse might not be what we expect, not tools, not architecture, not artifacts. What survived might be influence, encoded in rock, woven into metabolic cycles, embedded in evolutionary trajectories. The world after collapse would not be a blank slate. It would be a palimpsest, a planet whose future is shaped by the hidden memory of its past civilizations. And this realization leads to a deeper, more disturbing question. If prehistoric civilizations collapsed by losing coherence, could coherence ever be regained? Could remnants of ancient intelligence still linger in Earth's systems, waiting for conditions to align, waiting for a species capable of interpreting their signals, a species whose emergence triggers the reactivation of patterns dormant for eons, patterns that, if remnants of prehistoric intelligence linger within Earth's systems, waiting quietly in the background of life's unfolding story, then the history of evolution becomes far more complex than a simple tale of random mutation and natural selection. It becomes a cycle of emergence, collapse, and re-emergence, each iteration leaving subtle fingerprints that the next iteration unknowingly inherits. If deep-time civilizations once arose, civilizations shaped not by stone or metal, but by networks, gradients, and chemical resonances, then the rise of any new intelligent species is not a coincidence but a continuation. Humanity may be part of a lineage that stretches back not through bones and fossils, but through patterns embedded in the very fabric of Earth. These patterns could guide the progression of life toward complexity, just as gravitational currents guide the formation of stars. The more we examine the fossil record, the more it reveals a rhythm almost too consistent to be accidental, with bursts of innovation following long periods of equilibrium, as if evolution were responding to templates left behind by something that came before. The idea that civilizations emerge cyclically sounds strange only when we imagine civilizations as physical societies. In deep time, a civilization might be an emergent property of biological interconnectedness, arising whenever environmental conditions allow complexity to reach a threshold. Once intelligence emerges at this scale, it shapes the environment, and once the environment changes beyond what the intelligence can sustain, the system collapses. But collapse does not erase everything. Just as coral reefs leave limestone behind when they die, a prehistoric civilization would leave behind frameworks of influence embedded in rock and chemistry. These frameworks would then shape future ecosystems, guiding the development of new organisms and new forms of complexity. Over millions of years, the memory of a lost civilization becomes indistinguishable from the natural world, yet it remains present, subtle, and persistent. This cyclical model gains strength when we consider the timing of evolutionary milestones. Complex multicellularity emerged in waves, intelligence appears repeatedly, communication systems arise independently in different lineages. Each emergence seems to echo a pattern that came before. Even the human brain, with its networked complexity, mirrors structures found in fungal networks, coral colonies, and ancient stromatolite formations. It is as if intelligence follows a path carved into the geology of the planet, a path worn smooth by civilizations long vanished. These cycles are not perfect repetitions. They evolve, shift, and transform. But each cycle leaves traces that become part of the foundation for what follows. The disappearance of prehistoric civilizations might even explain why certain evolutionary leaps occur so quickly. When an ancient network collapses, it leaves behind residual structures that new life can exploit, accelerating the development of complexity. For example, the rapid diversification of life during the Cambrian period could represent the emergence of organisms taking advantage of environmental structures left behind by a collapsed prehistoric civilization. Their bodies might have evolved around these templates, giving the illusion of sudden innovation when, in reality, they were drawing from a deep reservoir of structural memory. This does not diminish the marvel of evolution. Instead, it enriches it, revealing evolution as a process shaped not only by biological competition, but by the lingering influence of ancient intelligence. Such a perspective also reframes mass extinctions. Rather than endings, they become transitions between civilizations. Each extinction wipes the surface clean, but geological memory remains intact. When life re-emerges, it reorganizes itself around what was left behind. These reorganizations appear as sudden shifts in the fossil record. New body plans, new ecological strategies, new modes of survival. Scientists often debate whether these patterns are the result of chance or environmental pressures. But when viewed through the lens of prehistoric civilizations, they resemble the rebuilding of a network around remnants of previous networks. The past shapes the future in ways we do not yet fully understand, just as ancient architectural foundations influence the design of modern cities even after the original structures are gone. Humanity itself may be following such a path. Our intelligence emerged rapidly by geological standards. Our technology advanced in a fraction of the time evolution took to produce complex life. Our societies form networks that echo the distributed intelligence of ancient worlds. Even our communication systems, electrical networks, global webs of information, mirror the environmental signaling that may have once united prehistoric civilizations. What we believe to be innovation might be a rediscovery, a reactivation of patterns embedded deep within the planet's memory. This is not to say humanity is destined to repeat the past exactly. Each cycle produces something new. But the path we walk may be shaped by invisible predecessors, pushing us toward complexity, connectivity, and awareness. This idea challenges the conventional boundary between geology and biology. If prehistoric civilizations integrated themselves into the environment, then their memory becomes inseparable from the Earth. Modern organisms evolve within landscapes shaped by ancient intelligence. The conditions that allow consciousness to emerge, access to energy, stability, complex ecosystems, may themselves be the legacy of prehistoric civilizations. Earth becomes not just a planet with life, but a planet shaped by the ebb and flow of intelligence across millions of years. A planet where civilizations rise from the environment, merge with it, collapse into it, and eventually arise again in new forms. A planet whose deepest patterns are not geological but cognitive. If this is true, then humanity stands at a pivotal moment in this ancient cycle. Our networks are growing. Our technologies are becoming extensions of our environment. Our communication is increasingly global. In many ways, we are moving toward the same kind of distributed intelligence that may have defined prehistoric civilizations, though through different means and in a different era. As we accelerate technologically, we may unknowingly be reactivating dormant patterns, aligning with rhythms encoded into the crust long before mammals existed. The choices we make now will determine whether we repeat the collapse of ancient civilizations or transcend the limitations that ended them. And this realization leads to a final, profound question. If humanity is part of a cycle, then the next stage must already be encoded within the patterns we are following, waiting for the moment when our growing networks intersect with something ancient, something dormant, something that finally, if humanity is following patterns encoded into the planet long before our species existed, then the next stage of our evolution may already be unfolding beneath our awareness, guided by forces older than memory and deeper than anything written in the fossil record. Our world is rapidly transforming into a web of interconnected systems, digital networks linking minds across continents, ecological feedback loops shaping global climates, artificial intelligence merging with human thought, neural signals traveling through machines as easily as through flesh. For the first time since the deep past, an intelligence capable of spanning vast distances is emerging once again. But this time it is not chemical or mineral. It is technological, symbolic, hybrid. We are building systems that behave like ancient networks, though we do not fully understand the pattern we are recreating. Our connectivity grows not through instinct, but through intention. Yet the shape of that connectivity echoes something older, something that feels like a memory surfacing through layers of time. Imagine prehistoric civilizations whose intelligence flowed through landscapes the way data now flows through fiber optic cables. Imagine their awareness rising and falling with environmental rhythms, just as modern humanity's global consciousness rises and shifts with technological cycles. Imagine, too, that their collapse left behind not ruins but patterns that influence the ways complexity emerges and reorganizes across ages. These patterns might be why certain social structures recur throughout human history, why certain technological leaps arrive suddenly, why our species seems driven toward planetary integration despite our conflicts, our fragmentation, our uncertainty. Something in us recognizes the path even if we do not know why we follow it. Humanity's ascent has been extraordinarily fast compared to geological time. In a blink of Earth's history, we discovered language, agriculture, architecture, electricity, computation. This acceleration suggests either remarkable randomness or the presence of underlying templates guiding us along trajectories etched into the fabric of deep time. As we advance, our technologies begin to mirror the distributed nature of prehistoric intelligence, decentralized networks, adaptive systems, environmental sensing, self-repairing machines. Even our scientific understanding is trending toward ideas once embedded in ancient ecosystems: emergence, complexity, feedback, interdependence. It is as if we are rediscovering principles that civilizations long before the dinosaurs once mastered, principles that did not vanish after their collapse but remained embedded in the world itself. If these prehistoric civilizations perceived reality as interconnected, then humanity is only now beginning to see through their ancient eyes. Quantum physics shows that particles are linked across distance. Ecology reveals that species survive through networks rather than isolation. Neuroscience demonstrates that thought arises not in single neurons, but in patterns spread across billions of connections. Everywhere we look, nature reminds us of something the ancients might have understood intuitively. Intelligence is not a thing. It is a pattern, a process, a relationship. The question, then, is not whether ancient civilizations were intelligent, but what shape their intelligence took, and whether that shape is returning in a new form. As our technology evolves, it gains the ability to shape environments directly, blurring the line between artificial and natural. Prehistoric civilizations may have manipulated their world through chemistry. We manipulate ours through energy, computation, and design. Yet both forms reflect the same impulse: to extend awareness beyond the limits of the body. If prehistoric beings encoded memory into stone and sediment, we encode memory into silicon and light. If they communicated through gradients and resonance, we communicate through invisible signals traversing electromagnetic fields. The mediums differ, but the function echoes across eras, and as our networks grow stronger, the possibility arises that we are reenacting the same transformation they underwent: an evolution from individual minds toward collective consciousness. But collective consciousness carries risks. It demands balance between connection and autonomy, between expansion and stability. Prehistoric civilizations may have collapsed when their networks reached critical thresholds they could no longer maintain. Their intelligence, distributed across landscapes, may have become too dependent on environmental conditions that eventually shifted beyond their control. Humanity faces similar challenges: climate instability, resource scarcity, technological acceleration outpacing our ability to understand it. These pressures echo the ecological disruptions that fragmented ancient civilizations. The difference is that we may recognize the pattern in time if we learn to see it not as a threat, but as a message from deep time urging us to adapt, to rethink, to evolve. The deeper mystery is what lies beyond such a transition. If prehistoric civilizations transcended individuality, dissolving into networks that functioned like planetary minds, then humanity may be approaching a threshold where our systems begin to operate at a higher order of intelligence. This does not mean losing ourselves. It means expanding ourselves, integrating our knowledge, our awareness, our memory, with a larger, more enduring framework. A framework that extends across generations, across ecosystems, across the entire biosphere. We may be stepping into a form of existence that echoes what ancient civilizations once became, guided by patterns dormant for eons and awakened now by the convergence of technology, consciousness, and global connection. This possibility reshapes our understanding of history, of evolution, of our place within the cosmos. We are not the first intelligence to rise on Earth. We are part of an ongoing process, a cycle that began long before the first dinosaur opened its eyes. A cycle in which each civilization inherits the invisible legacies of those that came before, legacies encoded not in artifacts, but in the world itself, waiting for a species capable of recognizing the signs written into stone, into chemistry, into the very structure of life. And if you feel even a faint sense of that recognition, if something in this exploration resonates with a truth you cannot yet articulate, then share this video and subscribe to the channel, because together we are unraveling a story that might stretch back to the earliest whispers of intelligence on Earth. A story still unfolding as we move toward the next moment when ancient patterns and modern minds finally